The laws of mathematics permeate the universe as the invisible framework binding the cosmos together. Reading that, have you ever actually stopped to consider the profound idea that abstract mathematical structures might be the invisible architects of reality itself? Like, what if the equations we're writing on chalkboards aren't just mere descriptions? What if they're the literal, rigid boundaries dictating what can and absolutely cannot exist?
Welcome to this explainer. Today, we're going to be exploring something genuinely fascinating together. We are diving into Julian Bouchelli's generalization of the free functional calculus. Now, I know that sounds like a mouthful, but it's basically a framework that takes incredibly complex operator theory and maps it onto the very structure of how systems, and hey, perhaps even reality itself, are fundamentally organized.
So, here's our roadmap for today. We're taking a step-by-step journey, starting with the rules of reality, moving into the non-commutative world, exploring classical free analysis, making a pretty huge leap into category theory, calculating a free derivative, and finally, unveiling the invisible architecture of the cosmos. Let's get right into it.
Section 1. The Rules of Reality, Foundations and Filters. We're going to start by looking at mathematical filters. Think of things like the Fréchet filter. These act as incredibly strict judges that basically keep the infinite and completely toss out or discard the finite.
Moving on to Section 2, the non-commutative world, where order matters. You see, in standard, everyday math, order usually doesn't matter. But as we'll see, in more complex frameworks, that assumption completely breaks down.
This really brilliantly illustrates the divide we're talking about. Over on the left, we have standard math, right? X times y equals y times x. Pretty simple. But on the right, well, in the realm of matrix math and operator theory, a times b definitely does not equal b times a. When the actual order of operations fundamentally changes your outcome, you can't just rely on standard polynomials anymore. You need an entirely new mathematical toolkit just to describe these functions.
Which brings us to Section 3, classical free analysis, adapting to size. To actually solve this whole ordering problem, classical free analysis steps in, and it's super cool because it allows us to evaluate functions across completely varying sizes of matrices. But to pull that off, we first have to define the domain, and that's a free set. Technically speaking, it's a graded set of matrix tuples closed under direct sums and conjugation by similarities. But, put more simply, it's basically a domain that lets us treat these wildly complex non-commuting matrices as if they were just abstract independent variables. It literally lets us bring comfortable classical analysis right into this wild new realm. Section 4. The category theory leap, generalizing the rules. So this is great and all, but what happens when those matrices aren't perfectly square? Well, this is where Julian Bouchelli used category theory to just entirely expand the rules. To make this massive leap, we use what are called functors. You can really think of a functor as a sort of, a structural translator between completely different mathematical universes. It takes objects and maps them from one category to another, but, and this is absolutely crucial, it does it without breaking the underlying architecture.
But here's the catch. Just translating isn't enough, right? We need consistency. And actually, that is exactly where a natural transformation comes in. Think of these as the intertwining structures that keep those translated mathematical universes perfectly consistent with one another. They're making sure that operations in one category act similarly to operations in another. Honestly, it's a real light bulb moment when you finally see how it connects the whole shebang.
If you look at the commuting diagrams here, notice how the arrows perfectly encode this relationship. We've got our initial state on the left, and then on the right, the state after applying a functor. By preserving that intertwining structure, which basically just means the path commutes no matter which way you travel around it, a free map acts as a functor that flawlessly preserves these natural transformations across totally different spaces.
So, bringing it all together, the absolutely crucial point here is that for a function to be considered a true free map within this generalized additive category architecture, it has to follow some strict rules. It must respect natural transformations, it has to respect direct sums, and it has to respect automorphic natural transformations, which is really just a fancy way of saying it respects its own internal symmetries. If it hits all those marks, it perfectly preserves the structure of the categories.
Section 5. Calculating the free derivative, lifting the calculus. Okay, so now that we have built this massive, highly abstract space of free maps, we have to ask, can standard calculus actually survive up here?
It's a really profound question. What happens when we take the derivative of a free map? Seriously, think about it. How could we possibly measure a rate of change, or a directional derivative, in a space of constantly varying, non-commuting dimensions and abstract categories? It sounds impossible, right?
Well, the answer is incredibly elegant. Through block matrix evaluation, classical calculus almost magically holds true. The free inverse function theorem and the Jacobian theorem prove that if a free function's derivative is non-singular, the mapping is totally valid and can be safely reversed. The math it scales perfectly. And that brings us to our final section, Section 6, the invisible architecture, math as reality. Let's bring this whole journey full circle now. Why does all this super abstract math actually matter to us? Well, because these rigid rules might just dictate our actual macroscopic reality. As highlighted in our sources on the personas of arithmetic, there's this quote: "The invisible constitution creates an invisible gerrymander, overriding localized paths." Now, what does that mean? Well, just as Arrow's impossibility theorem shows us that finite systems inevitably collapse into local dictatorships, the absolute boundaries of reality act kind of like a macro-level constitution. This huge transfinite boundary rigidly governs all our finite local paths. It basically swallows up individual variances just to maintain the ultimate topology of the whole system.
So ultimately, category theory and the free functional calculus, they aren't just abstract equations on a page. They actually provide the rigorous architecture binding our entire non-commutative cosmos together. They prove that the absolute laws of set theory and topology are, for sure, completely inescapable. Which leaves us with this final, somewhat provocative thought to take away from this explainer. We all act as the local dictators of our own choices, right? We feel like we possess localized free will. But if all our finite choices are ultimately bounded, filtered, and preserved by these rigid, transfinite free maps, are we actually writing reality? Or are we really just following the invisible architecture,